brief introduction. So my name's Jacob Quinn. I actually work at a company called Relational AI. We've been around for 4 or 5 years now. We use Julia as the core language for our product. We're building a kind of graph native relational database and doing some really cool things with that. And it's all in Julia, so it's really cool. We have a little Julia kind of specific team at Relational AI that focuses on improving the core language and then also the ecosystem and just kind of being a general support for the rest of the product team. And so that's kind of where I fit in. But it's super fun. There's, I think, 4, 5, 6 of us around. Casey's here with me. So if you're interested in relational AI, come find us and come talk, and we'd love to chat more about Julia. But beyond relational, I have been involved with the Julia community for a long time. So I got involved. I actually started using it like the weekend they publicly first released Julia, and I was like, hey, this sounds cool. I'm struggling working through these R scripts that are taking like 20 hours to run because I was trying to do this weird iteration thing, and I couldn't vectorize it just right. And I was also a very poor programmer at the time. And so I was like, hey, Julia sounds great. And I switched a bunch of my scripts over, and they all ran in 5 minutes. And so, it was an easy conversion for me. And so that's kind of how I got started in Julia, and I've just kind of stayed involved ever since. I actually don't have a CS background or never formally trained as a programmer or in computer science. And so Julia is unique because I learned how to program through Julia and just using it and coding and everything. So anyways, thank you to Bogomil for the first half of this. He covered a lot of great stuff. I'm going to be focusing on working with DataFrames. It says beyond CSV, but we are talking about CSV first because that's a big part of data ingestion, and it's a very common format when you're working with DataFrames. So we're going to talk about what the CSV package provides, and then we're going to talk about Arrow, and then we're going to talk about JSON data a little bit. So I think the bulk of it will probably be on the Arrow side. I'm definitely open if you have questions along the way, or something doesn't make sense, or I'm going too fast. Please feel free to raise your hand. I'm happy to make this pretty interactive. But yeah, let's get started. So I actually did these 3 parts. So the repo is here. This is the GitHub repo, JuliaCon 2023 tutorial. I actually have this in Pluto. So a little bit different flavor from what Bogomil was sharing, but very similar. It's kind of a Julia-specific notebook program. If you need help getting that set up, it's pretty easy. You just kind of go here and run Pluto. Oh, I don't have it there. Here. Oh wow, got an error going on. That's okay. But you basically add the Pluto package, and you just say Pluto run, and then it opens up your browser to something that looks like this. Okay. And then if you start it in the repo, the directory of the GitHub repo that I have up here, then it should show these same notebooks that you can just open. So the cool thing about Pluto is the notebooks are just Julia scripts. So you can see these are .jl files. And so if you open it up, I think it'll just start running everything, and it should install everything and kind of do all that package management stuff for you. That's the promise. So hopefully that works. I didn't actually test that on a separate machine. But Pluto is really cool. It has kind of a lot of stuff built in, and it makes it really easy to kind of put these together. So anyway, so I'm going to be kind of talking through some of the text that I have up here. I kind of meant for these notebooks to be very persistent and easy to use and reference beyond the workshop of here today. So I'm not going to just read them word for word, but I'll kind of talk through some of the things we have here. Obviously going to talk through the code that we're working here and the concepts. but feel free to come back to these and reference these, and hopefully they're helpful, beyond just what we're doing here today. As a note on the data that I'm working with, I did create 2 files that I'm mainly kind of focusing on for a lot of these data operations today. One is a really big one, well, really big. It's big-ish. It's about 350 megabytes compressed. It's gzipped. So if you click on this link, it should take you to a Google Drive thing that you can download that directly if you want. It's about 1 gig uncompressed. You can uncompress it or not. It doesn't really matter. CSV will read it either way the same. But then there's also a really small one that's like 20 kilobytes. And it's the same data schema. So if you don't want to like download a huge thing or you're constrained on space, you can just do that smaller file. And then all of these same commands should mostly work. There's one in the Arrow where we're trying to do this partitioning thing. So that might be a little weird. You have to change something. But otherwise, everything else should just work on either size file. The thing that you will have to change to get this to work on your machine is this path right at the top. So this is at the top of each of these 3 notebooks. You'll just set that path. And then everything else should kind of just work and run the code that's in the Pluto notebook. So anyway, here's mine that I've wrote to this compressed CSV file. And then I'm kind of reading that in to using CSV. So yeah, let's talk about CSV and what it provides. So the CSV package has been through a few different iterations over the years. The current API provides, it's not officially 1.0 yet, but it's unclear if we'll stick with this for a 1.0 or kind of smush them together somehow. But right now, there's kind of 3 main ways that you can process delimited data through the CSV package. And it's CSV file, CSV chunks, and CSV rows, okay? And they each have slightly different pros and cons and trade-offs and kind of depend on what your use case is and what you're using them for. So CSV file is kind of a more traditional interactive, at the REPL, I would say data analyst, data scientist kind of use of CSV. So it's when you call CSV file on a delimited file, it's going to parse the entire thing. It's going to do automatic type inference, figure out what the types of everything are, and try to be the most specific it can. And then it produces these columnar results. So the end result is you get these big long arrays of strongly typed values. And if it encounters a string along the way or something it doesn't recognize, it'll promote to that, and you can clean it up afterwards or whatever. But it kind of processes the entire file, and you get the entire results in memory. Okay, so that's CSV file. The result you get is very data frame-like. Okay, but it's just a CSV file object because we'll talk about this a little bit later. We don't need CSV to depend on the DataFrames package. As Bogomil talked about several times, we have this nice thing called the Tables package, which helps all of these different data formats, 2D things, talk to each other without needing to depend on each other, okay? Which is super great because if you've ever been involved in other language data projects, it's like we all have to roll our own CSV parser, and we all have to roll our own database connectors, and we all have to roll our own everything because, if I wanted to talk with everything, I have to do it myself. There's not like an easy way to like plug things together. So tables helps us to plug everything together without needing those explicit dependencies. And so the result is in CSV, we get this CSV file object, which by itself is pretty useful. And I can use that directly to process data if I wanted, or it's very easy to kind of put that into a data frame and do data frame specific operations on that. So we'll talk a little bit about that in a little bit. But that's CSV file. So it does automatic type inference for us, and it gives us these columnar results that is basically like a data frame. CSV chunks is a way for us to get very similar behavior to CSV file, but to take a large file and only process it in chunks of the file at a time, okay? So I might have a file with 1 billion records, okay, billion rows, and maybe I want to process them, 50 million rows at a time, okay? And I can split that up into however many chunks I want. Each iteration, as I iterate, I get a CSV file. So it'll do the full type inference, give me the columnar results for each chunk, but I'm only processing, chunks of that file at a time. So it allows me to kind of batch process a large file, okay? I put the star next to the low memory requirements here because it really depends on how much you chunk the file up, right? If you chunk it up into, a million chunks, then obviously you're going to have a lower memory footprint for each chunk, okay, that I need at each iteration and each time. If I split up a, 10 gig file into 2 chunks, that's still 5 gigs, per chunk. So that's, a little bit dependent on you and how you process it. Okay, the last option is CSV rows, okay, which is, as you can probably guess, a way to process CSV delimited files on a row-by-row basis, okay? And this is meant to be the lowest memory overhead possible. It's really moving line by line through the CSV file, and there's a way to allocate a single buffer that results get parsed into as you iterate through it. So it's a way to kind of try to avoid needing to materialize a full column, okay, of the results at a single time. You can just process that row by row, okay? And there was something else I was going to say about that, but I forgot. So we're moving on. Any questions on that? Does that help clarify kind of what those 3 things do for CSV? Great. Okay. So let's show CSV file real quick. It's very flexible in terms of what you give it. You can give it a file name, just a raw vector of bytes. You can give it a command object, okay, if you're running some kind of shell process that's going to produce CSV or delimited something. You can give it any kind of I/O. If you have a file on the web, you can just call http.get, okay, using the HTTP package, and that returns a byte vector of the response. You can just pass that directly to CSV, and that will download, or that'll parse, okay? So it's very flexible in terms of what you can give it as input. You can give it a compressed file or not, and it'll figure that out automatically for you, at least for gzipped things. And then for others, the codec packages are really good at saying, here's my compressed byte buffer, and here's your uncompressed byte buffer. It gives you the uncompressed, and then it can deal with that directly. So here's a just really easy example where I am calling CSV file. I'm giving the path of my gzipped compressed file. And in this case, I don't have an explicit header in the data. It's just a file of the data itself. And so I'm giving it the header here, okay? So I'm providing the header myself of the column names that I want to give it, okay, the labels. And then this is what I'm getting back. And you'll notice that this looks a lot like a data frame, okay? And that, like Bogomil said, like this is because the tables interface, it recognizes things that are table-like, and it can display them all in a very similar way, okay? So we get the column types here, we get the column names, we can kind of see that things were parsed into date and date time, okay? So CSV figured that out for us, okay? It said, oh, this looks like a date. I'm gonna parse it as a date, and it did the entire column. This last column over here says date time question mark, okay? That means some of the values were null or missing, and it detected that, and it said, okay, these are, union date time missing, okay, for the column type here, okay? So this is very data frame-like, and you can use it in, similar ways as a data frame. And so yeah, you can access the names of the column by doing f.names. You can see the types by doing f.types. The other unique thing that CSV will do by default is it uses a unique string type called inline strings, okay? These are fixed-sized strings that are not reference types, okay? So they're not pointing to the string data that lives somewhere else. They actually store the data inline, okay? So a string 15 means that there are 16 bytes, and the string is taking up sum of 1 to 15 bytes, okay, of those 16 bytes, okay. So you can kind of think of a string 15 like an int 28, 128, okay. So it's 16 bytes, and the actual string data is taking up some of those 15 bytes, and then there's 1 byte left to indicate the length of the string in those 15 bytes, okay. So it's kind of unique, but it does use those by default. It's controllable in CSV, whether you want regular strings or whatever. But they follow the string interface. You can do any other string operations that you normally would. The big advantage and why they are used by default in CSV is they avoid creating GC references for every single individual string when you're parsing, okay? Which is really great when we're dealing with really large CSV files, okay? We ran into lots of cases where you would parse a very large CSV file and there's many string columns. Every single one of those strings creates a reference in the GC, okay, where it says, oh, I need to track this reference in the GC, and then you would do an operation and the GC time goes really high. So if we can, in CSV, there's a threshold over which if strings are too long, we obviously won't do inline strings because then you get into the danger of wasting lots of space, or there's a high variance in terms of the length of the strings. But in CSV data, we also know that a lot of cases there are short strings, okay, and we can kind of pack them all together in a very efficient memory representation using kind of these bits, fixed size width bits for these strings, okay. Yeah. Oh, garbage collection. Yeah, so in Julia, it's a GC language, which we say. So memory is automatically tracked for you and garbage collected, meaning memory is freed for you. You don't have to manually free your own memory, as opposed to Rust or C, some of these other manually memory controlled languages, okay? Any other questions? Is that okay? All right. So yeah, we can see the types, we can see the names of the columns, and with a CSV file, we can actually, if we want, process it row by row, okay? It's columnar in its results, okay? So if I added one here, I can actually see all the values that are in this column, okay? And it's all there and it's fine. I can process that like a normal array, okay? But CSV file is also, you can also consider it as a collection of rows, okay? And I can iterate through those. And each row, I can just access the column by saying row.wage, okay? So here I'm iterating, I'm initializing a variable with the sum of the wage, okay, as 0.0. I'm iterating over each row in my CSV file object. And then I'm adding up, okay, plus equals the value of the wage column for that row, okay? And in Julia, if there are missing values, which there are some in this column, okay, we have this really easy function called coalesce, okay, which is just like SQL, okay, where I can say, hey, if this value happens to be missing, use this other value instead, okay? So if row.wage is missing, I'm going to use 0 instead, but that's what I'm going to sum up as my wage here. The reason I'm using coalesce is if I added missing to a float value, the result is missing, okay? So missing propagates through plus operations, and I don't want that, okay? I only want to sum up the non-missing, and so I'm just going to sum up 0, okay? And then at the end, I'm kind of manually rolling my own mean calculation here. I'm doing the sum of wage divided by the length of f, okay? And that gives me kind of what's the average wage in this column, okay? And we can see the answer up here, okay? So that's what I'm doing here. Is that okay? Or everything makes sense there? Great. Okay, the other thing that I can do that's very easy is I can use the statistics standard lib, okay, which is great. So I can just call mean over the wage column, okay? So I can reference the entire column just by saying f.wage, okay? But like I mentioned before, there are missing values here, okay? So if I just call mean on the column, I get missing, okay? Because the missing propagates, okay, through that mean calculation, okay? So instead, I'm going to use this other utility we have, okay, in base, which is called skip missing, okay, which takes any iterable and it'll actually skip over the missing values, okay, as I iterate through it, okay. So if I run that, I actually get a different answer. Who can tell me why I get a different answer than from what I calculated up here? What? Yes. Yeah. So up here, I was coalescing 0 for the missing values, and then I was taking the entire length of all the rows in my mean calculation. And here, I'm skipping those. So it's kind of like I'm removing the missing values, okay? I'm not adding 0, okay? So there's a difference, right? There's a subtle difference that I should actually think about if one makes sense versus the other, right? If a wage is missing from all these people, does it make sense to treat that missing as 0? Okay, does it? That's pulling my mean down, right? So that's something I need to think about as I do this, as I work with this data, okay? I like that thought process because I think you should always explicitly deal with your missings, okay? Does it make sense to actually coalesce to 0? This is probably actually a little dangerous, okay? Because it's affecting my calculation in a way that maybe I didn't intend, okay? So skip missing is probably the more correct thing that I want to do here, which is of people who have a wage that I know about, what is the average of those wages, okay? I'm not just assuming, oh yeah, let's just throw a 0 in there, okay? And then let's bring in data frames to the picture, okay? So I can call DataFrame directly and give it my CSV file object, okay? And what do I get? A data frame, okay? And it looks very similar to what I had with a CSV file. But it is a data frame, and I can do lots of cool data frame operations on it, okay? So that's fun. But what exactly happened when I did this, okay? Did I make a copy of the data? Are the CSV file object and the data frame sharing data now? Like if I updated the data frame, would it also update the CSV file and the columns of values it had, right? These are nested data structures. So it gets a little murky when we start updating nested values in nested data structures and we're sharing or maybe sharing data between those, okay? So let's check. If I say FID equals DFID, okay, it returns true. But is that actually telling me what I think it's telling me? That they're sharing data, or are they just equal in their values, okay? Well, let's check triple equals. Triple equals is false, okay? So I know that those are not the exact same column objects. Those are not the exact same arrays that are being shared between data frames and this CSV file object, okay? But I know that they are value equal, okay, which they should be, okay? I just said make a data frame out of this data, so they should be value equal, okay? But this is a distinction between double equals and triple equals in Julia, okay? Are they the same object, literally, okay? Or are they value equivalent, okay? Double equals in Julia is a value equivalent operation, okay? So they're not sharing data, and a copy was made, okay? But what if I didn't want to make a copy? Okay, what if I had this CSV file and I was doing stuff and then I just want to throw it into a data frame, not making a copy because I'm going to be careful and not like, make updates and then assume updates weren't made, okay? So how do I do that? Well, Bogomil kind of talked about this in the last time. I can pass copy calls equals false, okay? And then when I do this triple equals, I can see that it's true, okay? These are the exact same column objects, arrays, okay, that are in my CSV file object and my data frame, okay? So exact same column objects. Alternatively, in the CSV package, I actually have another function which is called CSV read, okay, which will do this for me automatically, okay? CSV read is a way for me to say, hey, I basically want to do what CSV file is doing, but instead of materializing it as a CSV file and then doing something with CSV file, like passing it to a data frame or something else, I'm going to give it a sync function, okay? And a sync function is getting into tables world, okay? But it's any function that can take a table's source, okay, and do something with it, okay? So in this case, DataFrame itself is a sync function, okay? It can take any table source and make a DataFrame out of it, okay? And so I'm passing DataFrame as the second argument to CSV read, okay? And what it's doing is it's materializing, it's building that CSV file object and passing it directly to the DataFrame constructor, okay? And a DataFrame is being constructed. So it's kind of putting those into one operation, making a CSV file, making a DataFrame out of it. I'm smushing those together into one operation, okay? Bogomil talked about the SQLite package and how there's a SQLite load function, right? I can pass any source to a SQLite load. I could do that here, okay? If I had a SQLite connection open database, okay, I could say, hey, pass this CSV file object to my SQLite load, connection and load it into the database, okay? And it would do that in one operation, okay, that's visible to me, parsing the CSV file, passing it to SQLite load, and it's getting directly loaded into the database, okay? Yeah, Bogomil.
It's probably faster than loading it directly to SQLite, maybe.
Are you saying versus what?
Versus direct load of CSV file into SQLite. If you don't want. So parsing it by CSV.jl should be faster for large files.
Yeah. I would imagine so. Yeah. Some databases. So what he's saying is some databases have their own, like in SQL, load this CSV file. Okay, and this is saying we're loading the CSV file using Julia and then loading into the database. Yeah.
So the CSV read function doesn't deals with the intermediary of CSV file. What if you call CSV file and then you do data frame and then inside a data frame call in a one-liner, would it be analogous, the same operation as the CSV.read?
Let me make sure I'm understanding. So you're saying if I took, for example, this and did like this?
Yes.
Okay.
Is it the same as CSV.read?
It's not. Yeah. So that's kind of what I'm trying to highlight up here is when I call CSV file, it's creating its own object, CSV file. And then when I call data frame on it down here, a copy is being made of those columns.
Even if they are in the same function call?
Even if they're in the same line, yes. Because semantically, like on a Julia level, right? When I do this, when I do this, what's actually happening is CSV file is, I'm making that function call, and then I'm passing the result of that function call to the next thing in your chain, right? In this pipe operator chain, which is data frame. So I'm essentially doing two operations, which is, this is temp, okay? And then I'm calling f equals data frame temp, okay? And that's literally kind of at a Julia level, what's the order of operations there, okay? So yeah, there's no difference if I'm using this chain thing here from whatever. And that's why we have CSV read, right? Because CSV read is kind of smushing those operations together, okay, in one, semantically smushing them together. It's still doing the full CSV operation and passing it to data frame, but it's doing it in a way that data frame knows, oh, I know a copy doesn't need to be made, okay? Correct, yeah, because there's no first object, right? We're not actually kind of creating that CSV file object itself and making a copy, so there's not extra stuff to garbage collect, yeah. Do the no columns, what do you mean by that? Oh, yes, yeah. So you're saying, yeah. So we're saying if we did pipe here, and then we said like x data frame, x copy calls equals false. Yes. So then no copy is being made. Yep, that would work. Okay, CSV, we talked about that. Okay. Any other questions on that? We'll move on to CSV chunks. Yeah, go ahead. No. Currently, we assume all the CSV delimited input is going to be UTF-8. Okay. There is a package called string encodings, okay, which can take one encoding and change it to another. Okay. And it's very easy. Like you give it a byte buffer and it gives you a byte buffer, okay, encoded. So this is kind of where we direct people for now. We could possibly try to make that more automatic within CSV, right? Where we try to detect. The problem is detecting encodings is not a guaranteed thing, right? So it's hard to say, oh, this looks like Latin, whatever, Latin 1, or this looks like WTF8, whatever. That's not a guaranteed thing. And so I hesitate to like try to do that automatically for people, and then it's the question of like, is that useful to at least provide as a keyword argument where they don't have to go to a separate package and download and call the encode themselves. We would just kind of have a path to do that for you within. It's probably worth it. So I think we could get there eventually, but up till now, we've just kind of directed people here and said, re-encode it yourself or use a shell program or whatever. But once it's UTF-8, then CSV file can process it. CSV actually doesn't care what encoding it is, but it's assuming that most of your delimiters and whatever are ASCII encoded. And so if it's that, at least it'll process it, but your results might be weird because Julia itself is assuming UTF-8, right, for the string data. Yeah. Any other questions? Yeah, Bogdan.
I have a question. How much precompilation can CSV currently do? Because I noticed that sometimes it's really fast, so it seems everything is precompiled, but if I have a slightly different file, I get much more compilation.
You should open an issue about that. We try to precompile a good chunk of CSV. So when you first load the package, it says precompiling CSV. It's actually going through the most common code paths of what you would encounter when you call CSV file or CSV read with various types and stuff. And so normally that first CSV load should be within a couple seconds, and then even faster from there. I actually worked with Tim Holy a little bit to clean a lot of that up and make that more of a streamlined thing. That's kind of plagued CSV package for a long time, these precompile times. I'm sure there's more work we can do to improve things. So it would be good to do another round of improvement on what we can precompile, what we should precompile, and then reducing that time to first X for the majority of files. Okay. Sometimes you're providing these really, maybe corner case, configuration options or parsing options that are more rare that we're not precompiling, and so then you would see a bigger, compilation cost when you're first calling CSV file. But we try to at least cover, it's kind of like an 80-20 thing. We try to, cover the majority of cases in our precompile so that it's fast for the majority of cases, and you're only paying the extra compilation cost when you have kind of a more esoteric scenario. Okay, so CSV chunks. I'm going to go a little bit quicker through this in CSV rows. They're not much different, but I want to make sure we get into the Arrow stuff because that's, I think, a little meatier. So as I said, CSV chunks is basically like CSV file, but I'm processing a file in distinct chunks, okay? So it provides a very similar interface to CSV file, okay? I'm calling it like this, CSV chunks. I'm giving it a path. I'm giving it the same header as last time, okay? And then the only other thing I can really provide here is this endtasks argument, okay? And this determines how many chunks I want to chunk the file up in, okay? So I could give this 10, I could give it 20, I could give it 1,000, okay? It really depends on me as a user knowing kind of the data and the size and then saying, I want to chunk it up by this. By default, it will use the number of threads that you have in your Julia session, okay? Which, is maybe a rough, good estimate, okay? But it's really in your control of saying, this is how many chunks I would like to process this data file in. Yeah, do you have a question? Okay. Yeah, it's not great. Yeah, I agree. It's not the most intuitive keyword name, but yeah. Anyway, that's what it is. So yeah. Anyway, by default, so we'll chunk it up, and then I can iterate through that object. So the object I get back is a CSV chunks object, okay? And the only thing I can do with that is iterate it, okay? And on each iteration, what I get is a chunk. It's really a CSV file object, okay? So what CSV is doing here is saying, okay, I'm going to chunk up this file. Here's the chunks. For each chunk, I'm basically just going to do the same thing I was doing with CSV file. I'm going to parse the whole thing, columnar results, do automatic type inference for you, and you get this fully kind of baked CSV file thing. I could turn that into a data frame if I wanted, okay, in each of these iterations, okay? I could be like, hey, I actually want a data frame of this chunk, okay? And I could do data frame things, with that while I'm iterating, okay? So it's a way that I can batch process kind of an entire big file, okay? So in this case, you can see I'm doing a similar operation I was doing before, okay? But for each chunk now, I'm calling the skip missing on the wage column, and I'm summing that up, and then I'm getting the length, and then I'm dividing here at the end to get an average. Yeah, it does. Yes. So it has the same problem as before. I'm actually mixing them here, I just realized, because I'm doing the skip missing on the sum, but I'm doing the length here. So it's all over the place here. What I should do is say like non-missing and do the skip missing here. And then I can like sum this and do the length on this, okay? Something like that, okay? That would be more correct. That's right. It should be when it has a length. I know. Did we not resolve that yet? We got to figure that out. If length is defined on the original iterator, it should be defined on the skip missing one, but it's not. Okay, yeah, we'll figure that out. Anyways, so yeah, I this was on a plane. I'm flying around. I was flying back from Greece. It was a long time. Okay, so anyways, you get the idea though. So yeah, that's pretty much CSV chunks. It's not anything too crazy. It's really taking the CSV file interface and saying, hey, you can apply this on chunks of a file instead of doing the whole thing at once, okay? Which, in terms of really large data files, if you have a really big CSV file, that can be really helpful, okay?
So is the type of chunk literally CSV file?
CSV file, yep. Literally CSV file. I could pass it to a data frame, load it into a DuckDB. I can do whatever I want because it's a CSV file. It does the tables interface. So I can do anything I want tables-wise with each chunk, okay?
Each CSV chunk is smart enough to be reusing the same buffer as your CSV rows, you have like a buffer that you keep rewriting into.
CSV chunks does not reuse buffers from chunk to chunk.
So
You're always allocating a new chunk. And as each chunk past chunks will be released, right? So the GC can free those and reclaim as necessary. But CSV itself is not doing any reuse of the buffers. It probably could and probably should, but that comes with additional challenges, right? Where we have to make sure that you're not trying to do stuff with past chunks on new iterations, right? Like that's why in CSV rows, we don't automatically reuse buffers from row to row by default, just because, what if you collect all those rows and then you're assuming that each row is valid when actually they're all pointing to the last row's values, right? So there is some danger in trying to be cute and avoid these extra allocations, but then users get in trouble because they're like, well, I thought each one was unique. It's like, well, they're not. Okay, you're reusing those buffers. So that's why we tend to not do that by default, but we could probably provide that ability in here. Yeah. Okay. Yeah, so real quick, we'll talk about CSV rows. The biggest thing to highlight here, okay, is that CSV rows does not do automatic type inference, okay? If we think about it, that makes sense, right? Because all CSV rows is doing is saying, open up the file, do some initial pre-processing of like how many columns there are and whatnot, and it does some of the same pre-processing as the others, but it's not trying to figure out what the types are, because we're assuming, okay, that we're optimizing for a case here where you're doing one pass over the file, okay? And in one pass over the file, I can't guarantee that I give you the right types, okay, of all the values, okay, of all the values in a single column, right? Take, for example, in a scenario where I have, you know, maybe my ID column here, okay, but the very last value here is a string, okay? So I parse through the entire file, and I'm like, it's an integer, it's an integer, it's an integer. I've really got this, okay? And we get the last value, and it's a string, okay? And maybe that happened so that it's actually string data, and I want that as string data, but I was assuming the entire file that it was integers, okay? This could be the example with like zip codes, right? US zip codes are all numeric, but then the last row is a Canadian zip code, okay? And it's got letters in there, and all of a sudden it's a string, okay? And actually, I probably want that as a string, right? Because some zip codes start with 0, and I just like ignored that when I was parsing an integer, okay? So it's those kind of operations where CSV file is going to say, oh, I got this, okay? I can promote, I can reparse if I need, and make sure that that's a string column, okay? CSV rows is just saying, no, 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 I'm not going to do any automatic type inference for you, but we're just going to assume everything is a string by default, okay? String or missing. But what you can do is you can pass types yourself, okay? If you know the types of the columns, okay? So in this case, I'm being very explicit in saying the wage column name is a float 64, okay? And so then it knows, okay, as I'm parsing these, I'll actually parse this column as a float 64, okay? And I can be really explicit. I can pass types as a vector. If it's a matrix-like CSV file, I can just say type equals float 64, and it'll assume all the columns are float 64. So there's some things I can do there that are flexible, okay? I can also pass a function to this types keyword argument, okay? And I can say, given a column name and a column index, I know it should be this type, okay? So there's things I can do that make it convenient, okay? But for CSV rows, if you want typed values, I need to explicitly pass that, okay? There is a kind of clever function that we do have in CSV, and I don't know if this is actually going to work, okay? But it's called csv.detect, okay? And it'll actually run the CSV type inference function on a string value for you, okay? So it's a way, if you were doing something that wasn't performance sensitive, okay, but I wanted to actually get the value of some of the columns, okay, I could just run csv.detect on a string value, okay? So by default, all the other values in this row are strings, and I could run CSV detect, and it would give me whatever it figured out, date, bool, date time, whatever, okay? Yeah, we'll go.
The question is, are there indeed use cases where CSV rows would be preferable over CSV chunks? Because it seems to me that batching always should be more performant.
It's a good question. So type inference does come at a little bit of a cost, right? Like I said, if I'm parsing these zip codes and I parse this entire column as integers, and then at the end it's a string, you know, I have to go back and reparse some of those values as strings to make sure it's a fully accurate, lossless, you know, string column, okay? Whereas in the CSV rows case, there are a lot of production scenarios that I've been involved with where I always know the schema up front of what the data is going to be. I know the exact column types. And so CSV rows can be nice because I can say, here's the column names, here's the column types. I'm doing one pass over this data, and I'm doing whatever processing, calculation, whatever I need, okay? And I'm ensuring that there's never, multiple passes over the data. There's no confusion or extra cost of type inference. CSV rows can be really nice for that.
Yeah, but then row is not type stable, right?
Correct, yeah.
So that was my issue, because to chunks you can also pass type information, just like you said for
Yeah, you can.
rows.
Yep. I have some ideas around that. Around making CSV rows easier to work with from a type stability perspective. Yeah. So I think we can get there. But I mean, it's easy enough now to be like, if I put this on there, I mean, that's going to be about as fast as you can get anyway, doing assert on the value as it comes out, because I'm storing this in an any box anyway. And so if I can pull this out and tell the compiler, hey, this is a float I'm missing, that's going to be pretty efficient. So there are ways, even right now, to manually make sure things are very fast, and I'm not paying a penalty of type instability. But I think there are ways to make that even easier and nicer in the future. Yeah. Any other questions? Yeah, so that pretty much wraps up what I wanted to show on CSV. I'll just talk really quickly about things that we're thinking about going forward. So this is one of them, actually, is thinking about this interface with CSV rows and maybe moving more towards a model. This has been a pattern I've been going to a lot lately in a lot of Julia packages, is flipping from passing my data to my function versus passing functions to my data, okay? And the Julia compiler being much more, happy with that process. So the idea here is as I'm, and this is what Bogomil is bringing up, I'm iterating these CSV rows. But this row object, once I'm dealing with it here, and I say row.wage, the compiler says, I don't know what that is, okay? When I called CSV rows, I mean, all you returned to me was the CSV rows object. It's not parameterized on the column types. I don't know what the value of this is going to be, okay? Unless, like I said, I'm asserting something about the knowledge that I have, okay? Manually as a user, okay? So in this case, I'm passing my data row.wage, which in this case is untyped as far as the compiler goes, and I'm passing it to this coalesce function, okay? So I'm passing my data to the function, okay? And for the compiler, that's hard, okay? It's saying, okay, I got a dynamic dispatch, I got a call coalesce with whatever this thing is, and then at runtime I say, oh, it's actually a float, and then I can go look up the coalesce float method and then pass it in. Oh, no, it's actually a missing value. Now I gotta go look up that and pass it to this. So there's a dynamic dispatch at runtime in each iteration here, okay, for this process, okay? So that's what we're talking about in terms of this type instability. If I do this assertion, okay, or if I structured my code like, val equals row dot wage, and I said if val is a float 64, sum wage 3 plus equals val, okay? If I did that, that's also going to be very efficient, okay? Because the compiler, once I asserted val is a float 64, okay, then it can know, oh, okay, val here is a float 64. I know that, and I know how to plus a float 64 with another float 64 all day long very efficiently, okay? So this is another way where I'm kind of manually asserting these types, okay? But that's what it takes currently to make this really, fast and efficient, okay? Which is good. I probably should have baked that into what I was talking about here today. But what I'm thinking about in the future is something where instead of iterating over the rows of this CSV row, I would do something like CSV rows on my path and then all my keyword arguments, okay, do row, okay? And what I'm passing here is a function to my data, okay? And even in this case, we'd still have type instability of like the individual column, okay? But maybe this would be like the values of the row or something like that, okay? The idea is that if I can pass the function to my data, then in CSV and the rows, application of that function, it can do the unrolling and the union splitting and whatever for you and apply that function in a type stable way, okay? And all your function has to do is say, okay, I'm a float, I'm a int, I'm a missing or whatever, and it can apply that, and it'd be very efficient. So something along those lines is one of the things I'm thinking about in terms of an interface change. Not really a change. I think we would still support this because it's very convenient, okay? But as a way to at least provide a really convenient way so that I don't have to do tricks like this myself, I could just pass my function in to do that for me. Another cool thing that we're thinking about that's already kind of out there and works is a package called newline lexers, okay? This is using some of the really fancy SIMD tricks that Daniel Lemire has been publishing a lot about. He has a package called SIMD JSON. I think he's done like a UTF-8 validation thing with it. I think he's done some float parsing using some of these techniques. So the idea is that there's these really powerful SIMD native instructions. I can operate on 16, 32, 64 bytes at a time, in one instruction, doing compares and different, operations. And because parsing a CSV file is basically going byte by byte and doing lots of comparisons and those kind of operations, what if we can vectorize that, okay? And we can do it in 64 byte chunks at a time, okay? So the newline lexers package is something we've been working on at Relational AI that we use in our data ingestion, okay? That takes some of those same techniques, but in Julia, and for now, we're just using them to do like the new line detection in a CSV file, okay? So we're using the SIMD techniques to very quickly process a file and say, give me all the new lines in an accurate, correct way, right? Because the problem with CSV is like, I could have a new line in the middle of a string, right? But we need to ignore that because that's not a real new line. It's just like part of the data, okay? So I'm ignoring those new lines and I'm only accounting for the ones that are like at the actual end of a row that signify, okay, I'm moving on to the next row, okay? And it does that very fast. It handles escapes and quotes and everything. But it's very cool and it's very efficient and it's using those SIMD instructions. So there's a lot of advantages there. So you can imagine that being incorporated part of CSV file, part of CSV rows, CSV chunks. We currently have another package called ChunkBase that is doing this. So it takes IO objects, it reads in chunks of those IO objects, it does the lexing, and then it calls basically CSV file on those, or CSV rows to process those really efficiently. So we have some ideas that are in the works. Currently, they're very like low-level manual things that we're using to do data ingestion at really high speeds. And part of that is because we know exactly what the machine type we're running these on, right? Because it's a production setting. So we can assume I've got AVX 512 on this machine and I'm getting the full leverage of like these SIMD instructions. So there's some challenges there of generalizing this so that like normal everyday machines, whatever setting, Windows, Mac, whatever you're running this on, can see speed ups and advantages to these kind of approaches. So there's some challenges to generalizing this, and then it's also a challenge of like how exactly do we fit this into the current CSV paradigm of CSV file and CSV chunks, CSV rows. How does that all fit together? So I think we'll eventually get there, but these are some of the things we're working on. I feel like we have a really good foundation for some fast new techniques that we'll incorporate in CSV, but I think we're still a little bit of ways off from actually seeing that in the end result. So. anyway, that's the CSV kind of portion of this. Any other comments or questions on CSV stuff? Okay, all right, let's talk about Arrow. We're going till what time? 4:30. Okay, we gotta move. We might not get to JSON stuff. Okay, we'll see. So to answer the question from earlier, I got way too much content. I wasn't sure, but now I know. Okay, let's talk about Arrow. So Arrow, I'll just give you a quick primer on what Arrow is. Okay, it's a data format that is specifically about the exact byte memory layout of data. Okay, that's unique, right? Because most data formats, JSON, Parquet, all these, SQLite, okay, they don't give you the exact how this looks in memory, okay? They're just saying we support floats, okay? What's a float? It doesn't matter. It's up to the language implementation, okay? Arrow says, no. A float 64 is 8 bytes of memory in the IEEE format and down to the exact bits of what each bit means, okay? So that's the difference, okay? As Arrow is saying, here's an exact memory layout for data, structured data, okay, in a columnar, way that every single language implementation, okay, Go, C++, Julia, whatever, is going to implement exactly, okay? And if you don't implement that exact memory, layout, then you're not Arrow, okay? Now, why is that important? Why does that matter? It's really about this zero copy, okay? That means that if I have a blob of memory in Julia, okay, that is Arrow data, I can take a pointer to that or mmap that array, okay, share that with a Rust process or a Java process or a C++ or a Go process, okay, and they can say, boom, this is Arrow data, and I know how to process that, okay? So it's literally providing a zero copy way that I can share data between processes, okay, on the same machine, okay? Or if I just send you a chunk of bytes, okay, to another machine, I can just take those bytes and say, okay, I know what this is. This is Arrow data. I can immediately start processing it, okay? So it's a little bit of a different mindset, right? Because most data formats, JSON, CSV, some of these others, we think about an explicit serialization process and a deserialization process, right? There's a difference between going from on-disk memory bytes that are serialized and then what I deserialize into my language, structures, okay, my language memory layout, okay? And there's some kind of translation that happens there. And Arrow is saying, nah, we're not having that. It's the same memory layout on disk, in memory, okay, that I'm transferring around. And what the languages do is basically interpret those bytes with structures. So your structures are pointing into those memory blobs and knowing how to interpret those bytes, okay? Yeah.
Two questions. Can you remind us what the IPC acronym is, and does Arrow take care of big endian and little endian issues?
Yes. Yeah. So IPC is inter-process communication. Okay. So that's what I was saying. Like different processes operating on the same data. Okay. And then yes, they account for little endian, big endian. That's part of the metadata of the Arrow file. So I can walk. I'll get right to it, but I'll include how it fits into that. Any other questions, real quick, on Arrow? Okay. So yeah, I'm working on the same data set. It's a CSV data set, okay? But the first thing I show here is how to put that into the Arrow format, okay? So Arrow provides an arrow.write function, okay? That I can provide it an IO buffer or an IO file object, IO stream, or a file name just as a string, okay? And then it will write that table, any table, okay? So a CSV file or a data frame or a SQLite table or whatever. It'll write that out into the Arrow format, okay? In this case, okay, as I walk through in these steps, I'm providing an IO buffer, okay, to the Arrow write function, which is like an in-memory IO object. I'm writing the Arrow data to it, and then I'm calling this take function on the IO buffer, which says, give me the raw bytes that were written to this IO buffer, okay? So these bytes up here, okay, all 1 billion of them, okay, this is exact Arrow data. This is what Arrow data is. These bytes laid out in this very specific format, okay? And these can be exactly shared with other processes, okay? I was gonna try and like show that in here by having like PyCall with PyArrow and like showing how you can like read those bytes, but it's kind of a pain to set up, especially like through Pluto and whatever. But I used to have round trip integration tests in the Arrow package where we did that. We would like spin up a Docker file with PyArrow and we'd actually read the bytes written from Julia and deserialize and redeserialize and back through Julia. So it was cool. But anyway, these are the exact bytes that we're getting when we write Arrow data. Question?
Yeah, I see the exclamation point there. Can you describe the mutation process?
Yeah. So it's just an IO buffer thing, okay? So if I have an IO buffer, okay, and then I write to that, okay, in my IO buffer, okay, there's data underneath there. So when I call take, oops, I deleted my cell there. When I call take on the IO buffer, I'm taking those bytes out of the buffer, okay, and now my IO buffer is empty, okay, it doesn't, you can't really see here. Like the size is 0 here, the pointer is at 1. So it's essentially like I mutated that IO buffer and took the data out of it. So that's the mutating that's going on there. Any other questions? Okay, we're moving. So what do we do with these bytes, okay, in Julia? I can call arrow.table, okay, and this is how I read Arrow data into a Julia structure, okay? Read, we're gonna talk about what that means, okay? So I get this structure back, it's arrow.table, okay, with 18 million rows, 7 columns, and then here's the schema, okay? This is great. This is just like the schema we had in the CSV file, okay? So that's what I would expect. It's got the same types and, you know, this is what I would expect, okay? So what is this arrow table thing, okay? What can we do with that, okay? Well, I can look at the columns, okay? Just like CSV file, just like a data frame, I can actually look at these columns, okay? So I'm pulling out a few of them here, and they kind of look like columns, okay? Like I can see data here that looks like values, but what are these names here, okay? Arrow.primitive, arrow.list, okay? What are those, okay? Well, I'm gonna walk through what happens when we call arrow table, and then that'll help explain what these fancy arrow things are, okay? So step by step, when I call arrow table, we first validate, hey, are these bytes arrow data, okay? There's a few validation checks they put in the format itself to say, hey, I'm arrow data, okay? So we check that first. Then we parse a schema message, okay? So arrow data is made up of messages that are laid out one after the other, okay? And the first thing that has to be in the arrow data is a schema message, okay? It tells me what kind of data is coming, you know, behind me, okay, in the next messages. So we first parse the schema message. That's going to tell me how many columns there are, the types, any metadata that's attached to the data set, okay? Whether it's little endian or big endian, whether the data is compressed or not, okay? And so from that schema message, I build up what to expect in the data messages that are forthcoming, okay? So then that's step 3. I keep parsing data messages until I exhaust the stream or the bytes or whatever, okay? And then the last thing that we're doing here is I'm building custom column views into the arrow data, okay? So I'm not allocating anything, okay? Not anything big at least, okay? I'm not parsing anything, okay? There's no additional processing, okay? I'm really just reading this schema message and then saying, okay, there's an int column starting at byte 20, and there's a float column that starts at byte 1000, and a string column that starts at byte 40,000, okay? And I return these little structs, okay, that are these, arrow primitive, arrow list, okay, that are basically views into the arrow data, and they know how to reinterpret that arrow data, okay? So that's what's going on when we read an arrow table, okay? And one of the things that I highlight here is that this arrow table process, oh, it's even faster now. It only took 600 microseconds, okay, to read this arrow data, okay? That's really fast. That's not very much time. That's not even a millisecond, okay? Versus CSV, when we were parsing that earlier, it took something like 4 seconds or 2 seconds or 1 second, okay, to read all that CSV data, okay? So this is really fast, and I actually have the data, and I can start doing things with that data right away, okay? And that's because we're avoiding all of the work that CSV is doing, right? CSV is saying, okay, I gotta open up the file, I gotta look at each byte, this is a float, I gotta parse that into a number, I gotta read this string, how long is it? Oh, there's escape characters, I need to unescape it, okay? So CSV is doing all this work for each row. Granted, it can do that very fast, and we're trying to optimize that, okay? But in Arrow, that's not even, we've taken all that out of the equation, okay? Because we're saying, here's the exact memory layout, okay, of all these floats end to end, and you're just saying, reinterpret those bytes, okay, as a float64 array, okay? So it's very, very fast because there's no deserialization, okay? There's no allocating, it's just reinterpreting bytes that we already know is Arrow, okay? Any other questions? Yeah. Mm-hmm. Let's talk about it right here. That's the next thing, okay? So that's great, but can I use this arrow data in a data frame, okay? Let's try it. Data frame on a table. Yeah, I get a data frame, okay? Now, what's actually happening here, okay? Is there a copy being made? If I say table.id equals arrow df_id, triple equals, that's true. This is the same data, okay? And this gets to part of a very important part of the arrow data, which is it's immutable, okay? You cannot mutate arrow data. Once it is written, it is final, it's immutable. I can't change that arrow data, okay? Which may seem restrictive, but it allows us to do things like this, okay? Which is, yeah, let's just give these columns data frames, okay? Because I know you're not going to change anything in the data frame that then will affect you later in some other way that you weren't accounting for, okay? Because it's immutable. You can't change that data as long as it's actually an arrow view into the data, okay? So arrow data is a columnar analytics focused data format because it's extremely fast sharing, serializing, deserializing, okay? And then I can process those results knowing that the data is immutable, okay? I can assume that and take optimizations based on that, okay? But it is immutable, okay? So I can't change that. If I want to change that, I have to make a copy, okay? And then I can mutate and save a new arrow block of that data, okay? Yeah.
I have a question. Why have you decided to use string type for string service, not some custom string type?
It's a good question. The arrow format, we could probably use a custom string type that is itself like a string view into the data, and we should probably do that. But when I was originally writing this, there wasn't a great option for that. I think there are better options now with like inline strings or like the string views package that would make that a lot easier. But at the time, it was like, we just need strings back. So we're just making strings from the string data that's in there. Yeah. Any other questions?
So DuckDB is really fast because they have also this column-based view into data that's homogeneous. Arrow has that too. But what else? Is there something that Arrow has that DuckDB doesn't when it comes to like analyzing columnar data?
So Arrow isn't an execution engine at all. it's not doing anything for you. It's just the format, right? So the value that DuckDB brings, and you can actually store your data as Arrow in DuckDB, okay? The value that DuckDB brings is it has all of these processing operations on Arrow data, okay? And it's funny, okay, that you bring this up because most of the other language implementations for Arrow not only have to implement Arrow deserialization and serialization, like interpreting Arrow bytes, but they also have to build entire engines to process the data, okay? Because they're like, whoa, I have this custom, Arrow primitive thing that's in Go, and now I need to actually write a thing that knows how to sum up values in an Arrow primitive, and I need to write a thing that knows how to calculate the average or the mean or the standard deviation. I need to write all of these operations to process Arrow data, right? And in Julia, we don't, okay? It's really great because we just say that an Arrow primitive, okay, this thing is an abstract array, okay? And you can do lots of cool things with abstract arrays, okay, right? You can just sum one of these things up, okay? And that works, okay? All of these things are so generic in Julia that we don't need to write an entire processing engine on top of the data format kind of reader-writer, okay? Which is very convenient, right? Because that means we can just stick these things in a data frame and do group by aggregation thing, joining with the things on the Arrow data itself, and I can process things like that, okay? I can use the full strength of data frames, and it doesn't even know about the Arrow format, okay? Very cool. And it makes the Arrow package's job much simpler than any other language implementation for the Arrow format. Okay, yeah, I wanted to highlight really quick something that Bogomil brought up, which is this copied columns thing, okay? And this is how Arrow actually signals to data frames that it doesn't need to make a copy, okay? Because Arrow is saying, this data is immutable, you can assume it's copied, just go use it, okay? Because when data frames doesn't see this, and by default copy calls is true, then it'll actually make a copy of each incoming column, okay? So this is how Arrow signals, okay? It's by overloading this tables.columns function, and it wraps the Arrow table in the copied columns, okay? So that's how it knows, oh, I don't need to make a copy here. I can just assume ownership of this data, because when I try to do a set index, okay? So here I'm on the Arrow data frame. I'm trying to like change the value of a column here. It's just throwing an error, okay? It's saying, whoa, 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 you can't change this data, okay? So you would have to make, oh, I didn't have an example here, but you would have to just copy that column into an actual array, and then you could change those values, okay? Let's really quickly run through a few more things here, and we'll finish up, okay? So the other cool thing that Arrow, like I said, the process it goes through is read a schema message and then read data messages, okay? Each data message is called a record batch, okay? It's like a row group in Parquet, okay? So here's an example where I'm doing this partition on my data frame. This is the big one, it has 18 million rows. So I'm splitting it into 1 million row chunks, okay? This data frame, and then I'm writing those out. When I read the table back in, it just looks like a normal table, okay? Because by default, the Arrow package, when you say read a table, it's going to lazily concatenate all those row groups for you automatically, okay? So it just looks like a regular table. It uses this utility array called the chained vector to lazily concatenate all those. So it's like a one big flattened array, okay? But the other thing we can do, I'm going to skip over this, is there's also a, oh man, it's way down here. There's also an Arrow append function, okay? So it's like the write function, but I can give it an existing IO or block of Arrow bytes and say, actually, I want to append one more data message, okay? And it'll validate to say, okay, is the data you want to write the same schema as the schema that was originally wrote. So it does some validation there, but then it'll just append one more data message there. It's really convenient, okay? If you had a data set that was updating on a regular basis with new rows, I could just be writing to a single file if I wanted that was just adding one more data message there.
For clarification, you can't change an existing row, but you can append zeros.
Correct. Yep. Okay, let's pick one more thing to talk about with our time here. Yeah.
You also can't load a piece of Arrow and bring it back in. It has to take in the whole table back into it. Whenever you save all that data as a write, right? But then you redo it back in. Could I have read in a portion of it in the same way as CSV?
Say your question one more time. Sorry, I'm not.
So you can read row by row in CSV.
Uh-huh.
You can skip rows based on anything you might want.
Yeah.
Same thing with Arrow.
Almost. So let's take that as our last thing we talk about, which is Arrow Stream. Okay. So there is a way, if I wanted to iterate over the data messages. Okay. And that's what Arrow Stream does. Arrow Stream will say, okay, let me take this Arrow data, read the schema message so I know what to expect, and then I return immediately. So I didn't read any data messages. Okay. But then as you iterate, okay, the stream, so I say for table in stream, each iteration is saying, I'm going to read one data message. And then I return an arrow table of just one data message, okay? And then you can do whatever you want with that. You can put it in a data frame. Here, again, I'm doing this wrong thing of skip missing and doing the length of the table, okay? But I can do whatever I want with just that one data message, however big that is, okay? And then on the next iteration, it's just going one more data message until we're out of data messages, okay? So that's Arrow Stream. The other thing I walked through here was support for custom types. So Arrow actually has pretty good support for this, and through the Julia interface, you can make custom structs, write them out, read them back in, okay, and it just kind of works. You can deserialize them as person, this custom struct, and then it also supports the metadata stuff that Bogomil was talking about. That's really great. So the one thing we do need to add support for is that I started, and then someone else said they wanted to finish it, and then they never did. And so I was like, okay, I should have just done it. Is the C data interface. So currently, this isn't really that important, but currently the format, the metadata for an Arrow table is written in flat buffers, which is like a zero copy, serialization thing. But they also have the C data interface, which it just writes it out in this like simple text-based shorthand. So you have to parse a little bit, but it's just the metadata, so it's really fast anyway. But it's actually what DuckDB prefers is the C data interface for the Arrow data to interchange. So anyway, we need to finish support for that, but it's not like that big of a deal. And then there's also this Arrow flight thing where you can integrate with gRPC to send data over there. But I mean, it's essentially just slapping an efficient HTTP2 server on top of your Arrow data to share back and forth, okay, and use some authentication. So anyway, we hopefully will get there eventually, but they're kind of minor, Arrow things. So let's take maybe a couple more questions and we'll wrap it up. Not easy. Nope. Because you can't, it's immutable, right? Yeah, so you can read the data into a data frame and you could call filter on that, and it's going to create new copies of those columns, and then you could write that back out into Arrow data. But it's really not meant for heavily mutating kind of workloads.
Can you partition Arrow data on a column value?
Yes. I mean, so you're not affecting the physical partition of the data that's written, but if you're doing data frame operations, group bys based on a column value, yeah.
And then you can just read in that one set of data.
Yeah, that's fine.
Just a comment. Normally, if you have Arrow data, you just filter with view through, and you have a view with the rows you don't want without copying.
Yeah. Yeah, so like a lazy, it's like a filtered view into the Arrow data. Yeah, it's very efficient. Yeah, Lilith?
Is the header, like the length, mutable in Arrow data?
You're saying like the metadata of the Arrow? No.
And okay, but you can add more messages after the fact.
You can add more data messages, yes.
And is the length operation O of 1?
Over the entire like Arrow stream of things? Messages, yeah. Which, yeah, the data messages themselves are very cheap because you've already parsed the schema message. So each data message is really, the metadata of a data message is like, here's my 10 byte offsets for the columns. And so it's very cheap to navigate each data message. The schema message takes a little bit more because you're looking at all the columns and types and endianness and all that kind of stuff, compression and all that.
When you mentioned that Arrow format is easy for intercross communication, I initially thought, okay, you get the data, and then one process modifies that data, and then some other process modifies the same data.
Yeah.
And then you said, oh, it's in good. So how would IPC schema work with that?
Yeah, it's a good question. So I didn't necessarily mean modify the data and then like share it back. It's more like I'm sharing this data with you, you're calculating something on the data and then sending that back, or you know, different processes are calculating different things, but it's all on the same data, okay? Like I said, if you are modifying the data, you can't modify it, but if you're changing things, you're then creating a new set of Arrow data that could then be shared back, but it's a new copy, it's a new set of Arrow data.
So, and then how will we integrate this kind of things? We'll have to have a server that only.
So yeah, that's what this Arrowflight helps with, is providing kind of an explicit client-server interface for Arrow data. But you could just do that through shared memory between processes, or named pipes, or however you wanted to kind of shuffle things around. Named M-maps, like there's different ways you could share the data. I don't know if anybody's used this with Spark. Does Spark support like native Arrow data ingesting? Okay. Yeah, I don't know that I've seen anyone explicitly use like the Julia with Spark. But we've done a lot of interop with Python and C++ and some of the other language implementations that are in the official like Arrow repo. So, yeah. I'll just mention really quick. So I have this third part that we didn't get to. It's about JSON data. It's pretty simple. Like I said, I think this is easy for people to walk through. The JSON is really the simplest of all of these in terms of data, because JSON is a very simple format, okay? But I will say that on Thursday, I'm going to be talking a little bit more in depth about what I think we can do with JSON, just kind of future of that. So if you want to come Thursday, we'll talk a little bit more about JSON. But yeah, happy to chat more about things. But yeah, thanks for coming to the workshop today.